Albert Einstein once said, "The theory of relativity occurred to me by intuition, and music is the driving force behind this intuition." My parents had me study the violin from the time I was 6. My new discovery is a result of musical perception. Music, he believed, was more than an art form. It was a way of thinking and discovering. So how did music allow Einstein to formulate his genius theory? What does music do to your brain? As I play Chopin's Fantaisie Impromptu, fireworks are going off in my brain. Studies have shown that playing an instrument engages more of the brain at once than any other activity that we know of. That is, nearly all areas of the brain are working to produce the ethereal, universal language of mankind, music. The piano is often considered to be the embodiment of virtuosity, along with instruments like the violin and the cello. Motor and sensory processes are obviously essential for musicians, but what exactly makes these functions run? What roughly happens within the brain? The occipital lobe, specifically the visual cortex, is responsible for reading the sheet music and allowing me to visualize the keys. The auditory cortex is located in the temporal lobe and is highly active as I play. It is the first stage of auditory processing. The primary auditory cortex processes the basic components of sound, such as pitch, volume, tone, and timbre, which is what differentiates the sound of, let's say, a horn and Mr. Litton's soothing voice. The superior temporal gyrus, or STG, is where sound is processed at higher levels, such as melody and harmony, which is processed in the right hemisphere, while rhythm and temporal aspects are processed in the left. The somatosensory cortex is located in the parietal lobe and is responsible for processing sensory information related to touch, pressure, temperature, and pain, playing a crucial role in my ability to control dynamics and feel the position of my fingers on the keyboard. The thalamus ensures that these regions receive the proper sensory information by acting as a relay station for the sensory signals. The hippocampus allows me to recall how this piece goes. It allows me to memorize and recall musical structures, patterns, and melodies, while other regions of the brain allow me to automate the actual physical execution, otherwise known as building muscle memory. The prefrontal cortex, located in the frontal lobe, is responsible for higher order cognitive processes and initiates the voluntary action of playing the piano. It is why I do this right here. It may have been subtle, but I made deliberate decisions to slow down, speed up, get louder and softer, and even delay a few notes in my right hand. It plans and applies expressive musical choices and decision-making while I play. Some are pre-planned, and some are just on the fly. The premotor cortex and supplementary motor area plan and organize the movements of my hands beforehand, and coordinates timing and initiation of movements with the primary motor cortex. The supplementary motor area also plays a role in bimanual control, ensuring that both my hands are coordinated. The primary motor cortex is responsible for the movements of my hands, sending signals through my spinal cord to the muscles in my fingers. The left motor cortex controls my right hand, while the right controls my left. Repeated practice strengthens neural connections within this area, which results in muscle memory. We'll get into this more later. The cerebellum fine-tunes motor movements, ensuring that the movements are smooth, accurate, and synchronized. The basal ganglia, found deep inside the brain, helps regulate movement, but also handles pre-learned motor programs and sequences, playing a major role in muscle memory. The cerebellum also continuously monitors the motor output and compares it to the intended movement based on sensory feedback and motor plans from the motor cortex. If there is any mismatch, the cerebellum sends signals to the motor cortex to make corrections and micro-adjustments. The corpus callosum is a bridge that connects the two hemispheres, allowing for inter-hemispheric communication and coordination, facilitating synchronization of my two hands. Lastly, The brainstem and spinal cord relay the motor commands to the muscles through neurons. Though these systems and processes are simplified, they all come together like one glorious orchestra, each playing distinct roles while harmoniously communicating with one another. We now have an orchestra, but something is missing. The conductor, the driving force behind music, its very essence. Now, what you might have felt there was a natural high from the climax of Rachmaninoff's Piano Concerto. This is because music, whether listening or performing, triggers the release of neurotransmitters associated with pleasure, such as dopamine, serotonin, and endorphins. Each play distinct roles in the euphoric experience. Emotionally intense sections also activate the sympathetic nervous system, leading to physical responses such as increased heart rate, breathing, and the release of adrenaline. This is why those climactic moments feel so exhilarating. You know, I've always wanted to play with an orchestra, but I don't have an orchestra. What I have, though, is a phone with a recording of an orchestra that plays excessively fast. In an experiment in Carnegie Hall during Yuja Wang's Rachmaninoff Marathon, the heart rates of Yuja, the conductor, the orchestra, and the audience were monitored. Astonishingly, their heart rates displayed synchronicity with a collective increase during emotionally intense sections. This synchronization reflects the powerful, shared experience that music can create. Music also engages the parasympathetic nervous system, which counters the fight or flight response from the sympathetic nervous system. This activation suppresses the hypothalamic pituitary adrenal axis, responsible for releasing the stress hormone cortisol. This dual activation allows music to both energize and relax, making it a unique, emotional, and physiological experience for both listener and performer.
Okay, you're starting way too early. You are too fast, sir. Too fast.
As I mentioned earlier, emotion is a neurological equivalent of a conductor, driving and amplifying cognitive and motor functions. Let me illustrate this with a scenario. Imagine two pianists of equal skill level. However, one is living the best day of their life while the other just had a breakup with their schnookins. And on top of that, a long day of ruthless torment from Mr. Litton. Both pianists are to perform Chopin's melancholic and heartbreaking prelude in E minor in front of an audience. Which pianist do you think will have a better performance? Now, as long as the heartbroken pianist isn't in a mental hospital after surviving a day with Mr. Litton, his performance will most likely be far more emotionally compelling, touching the hearts of the audience. But why? Well, music, whether listening or performing, engages the limbic system, the brain's emotional processing center. This includes key structures like the amygdala and anterior insula. The amygdala is pivotal for processing emotions and connecting music to past emotional experiences, making pieces evoke vivid memories or feelings, in this case, a heartbreak. The anterior insula fosters self-awareness of these emotions, whispering to the pianist, "You're sad, sad and alone, forever and ever and ever." The amygdala also communicates with the prefrontal cortex, specifically the ventromedial prefrontal cortex, which integrates the emotional signals sent from the amygdala and influences creative choices during the performance. The limbic system also connects to the motor cortex, influencing the pianist's touch, resulting in a more emotional performance. This emotional cognitive interplay shapes the pianist's expressive choices, whether subtle or grand, deliberate or subconscious. The pianist literally pours their emotion into the music. Lastly, the mirror nervous system also activates both in the pianist and the audience. For the pianist, the mirror neurons enhance emotional expression and refines their cognitive interpretation of the music. For the audience, these neurons facilitate empathy, forming a deeper connection to both the music and the performer. Subtle cues such as the pianist's facial expressions or nuanced dynamics evoke shared emotional responses, making the performance a profoundly moving experience. Now that we have established the conductor, I can now show you how this orchestra operates while I butcherly play a section of Chopin's Coda in Ballade No. 3. Firstly, my prefrontal cortex sets my intent to play and engages in decision-making as I play. The hippocampus recalls the musical and interpretive details and emotional context of this section, ensuring that I remember not just the notes, but how they are meant to sound. Meanwhile, my premotor cortex and supplementary motor area organize the sequence of movements required to play, including bimanual coordination. Because I have memorized this piece, my occipital lobe no longer processes sheet music. Instead, it processes visual information about the keys, providing a spatial map for my hands to follow. My basal ganglia and cerebellum work together to help automate the motor process by recalling the muscle memory I have developed through practice. For example, my basal ganglia, specifically the putamen, handles the repetitive octaves in my right hand that you will see later, freeing up cognitive resources so I can focus more on my left. The cerebellum monitors and recalls the precise details of tempo, rhythm, and dynamics, ensuring my execution aligns with my intention. The primary motor cortex executes the movements of my hands, fingers, and arms, guided by the stored patterns in my basal ganglia and cerebellum. Simultaneously, the cerebellum fine-tunes these movements, allowing me to achieve delicate adjustments, such as emphasizing the melody notes in my left hand by applying slightly more pressure. The music engages my amygdala and anterior insula, enhancing my connection to the piece and influencing spontaneous musical choices. These structures communicate with my prefrontal cortex and motor areas, creating a feedback loop between emotion and execution. My brain is constantly processing sensory information, and my cerebellum adjusts accordingly to the inputs from my fingers, ears, and eyes. That jumbled mess of wrong notes was because the neural pathways in my basal ganglia and cerebellum are not yet fully refined to handle the coda at faster tempos. At higher speeds, the primary motor cortex must send signals more rapidly and with greater precision. Without sufficient repetition to strengthen these neural pathways, errors are more likely. To compensate for the lack of control and fluency, tension arises in my hands and forearms, further contributing to inaccuracy and lack of control. With consistent practice at gradually increasing tempos, these pathways will strengthen, reducing tension and enabling smoother and more precise execution. So in 20 years. Wow, that is a lot to unpack. To finish us off, this is a recording of me playing Claude Debussy's Clair de Lune. Anyways, playing an instrument truly engages almost every region of the brain. It's like a full-body workout, but for the brain. This workout causes lasting, beneficial changes in your brain structure and chemistry. Musicians' brains show increased neuroplasticity, which is the brain's ability to modify or create neural pathways and synaptic connections, a process called synaptogenesis. This increased plasticity allows the brain to better adapt, learn, and recover. Additionally, musicians often have more gray matter, which are neural tissue containing unmyelinated axons. More gray matter means more neurons and connections, which translates to improved cognitive abilities, enhanced motor skills, better emotional regulation, and even a reduced risk of neurodegenerative diseases like Alzheimer's. Playing an instrument also sharpens information and sensory processing. Music demands rapid and accurate sensory and cognitive processing simultaneously, boosting the brain's processing speed, working memory, which is the brain's ability to hold and manipulate information temporarily, and executive functions. This multisensory integration encourages cross-modal neural connections, also known as cross-modal plasticity, which is a type of neuroplasticity, where the brain links sensory systems to create a unified experience of sound, sight, and touch. Music combines the linguistic and mathematical expertise of the left hemisphere with the creative right hemisphere. This collaboration increases the volume and activity of the corpus callosum, facilitating faster communication and more diverse neural pathways, fostering better coordination, creative problem solving, and synchronization of bimanual tasks, such as typing or this right here. Okay, show off. Several other structures were also found to be larger in musicians, such as the motor, auditory, and even prefrontal cortex. A study done by Dr. Sylvian Moreno found that musical training in children improved speech, reading, and language abilities and dramatically improved their verbal intelligence scores after only 4 weeks of training. These children also became more sensitive to changes in intonation, which helped them interpret and understand others' emotions better. Another study by Kirshner and Tomazello in 2010 showed that playing an instrument fosters empathy and pro-social behavior. Music also strengthens the connection between the prefrontal cortex and the amygdala, improving emotional regulation and response to stress. Finally, musicians show enhanced memory functions, creating, storing, and retrieving memories more efficiently and effectively. Memory serves as many disparate functions. There is sensory memory, which is how I know how every object in my room would feel. Procedural memory, otherwise known as muscle memory, like riding a bike or shooting a basketball. Semantic memory is the memory for facts and general knowledge, such as the mitochondria is the powerhouse of the cell. Episodic memory is the memory for specific events or episodes, like that time I completely butchered a piano performance. Spatial memory is the memory for the location of objects or landmarks. And autobiographical memory is essentially what makes you, you. It's how I know my favorite color is green, and why I'm scared of spiders, and how my favorite subject is any class without Mr. Layton. Playing music integrates multiple memory systems: auditory, visual, somatosensory, procedural, and semantic memory, strengthening the brain's ability to store and retrieve information. This, along with increased gray matter and connectivity, enhances both short-term and long-term memory. Well, there you have it. Now you know what happens every time a musician plays their instrument. An intricate symphony of motor, cognitive, and emotional processes take place in the tiny little universes residing within their skull. Music is far more than just sound. It is a profound expression of human ingenuity and complexity in our very soul. Well, what are you still doing here watching this Bio 12 project? Go pick up your instrument and start practicing.